Welcome to this video on the remainder theorem, factor theorem, and rational root theorem. Before we go into those, I want to review synthetic division, which you should have seen in Algebra 2. The first thing you want to do is take the x minus 2 and set it equal to 0, and that's what your x value equals. So I'm going to put that in a little box by itself. Then I'm going to take each of the coefficients and write them down with their signs. Then I'm going to leave a space and draw a line. First step is always bring down this first number, and then I'm going to multiply what's in the box with the number that's under the line. So 2 times 2 is 4. Then I'm going to add the 4 and the 4 and get 8. Then 2 times the 2 in the box times the 8 gives me 16. I'm going to add those together, I get 13. 13 times the 2 in the box is 26. Add those together, I get 21. So this leaves me with a polynomial with one less power than I started with. So I started with an x cubed, so it's going to leave me with a 2x squared, and then an 8x, and I just decreased the powers by 1, and a 13. This number, the 21, is my remainder. So you can write that as the number over what you divided by, which was x minus 2. So that's how you do synthetic division. You always bring that first number down, and then it's multiply, add, multiply, add. All right, let's get into the new stuff, the remainder theorem. If f of x is a polynomial function and is divided by x minus c, the remainder is f of c. Okay, so what does that mean? Let's take an example, and hopefully that'll make more sense. So I have this function, f of x, and I want to divide it by x minus 4. The remainder I get will be equivalent to if I did the function, the value of f of 4, and I substituted in 4 for it. Okay. So I'm going to do synthetic division. It's set up, it looks a little like long division in this. It's just how I could write it in PowerPoint. All right, so I'm going to bring the 1 down. So bring that down, multiply, add, multiply the 2 and the 4, get 8, add those, I get negative 7. So f of 4 is equal to negative 7. Now you might say, well, why can't I just substitute in the 4 like I have shown right here and do it out? Sometimes when you get good at synthetic division, especially if you get higher powers, like if I had an x to the 5th, sometimes the synthetic division can actually be faster. So the remainder is the same as if I substituted in that value. And also remember, if it's x minus 4, you put in a positive 4 in this box here. And if it's a plus, if it was a plus 4, you'd make it a negative 4 there. All right, we're going to another theorem because these all kind of come together into one magical event. All right, so we have the factor theorem. And if we have a polynomial again, and we divide it again by an x minus, plus or minus a value, if the remainder is 0, then what we divided by was a factor, because we got no remainder. All right. So let's do x squared minus 2x minus 15, and we're going to divide it by x plus 3. So right away you might see that it is a factor, because if I were to factor this polynomial, I would actually get x plus 3, x minus 5. So right away, you're like, yeah, that's a factor. 2 ways to see if it's a factor. You can substitute in x equals negative 3, because that's what it would equal if I set this equal to 0. And if that equals 0, it's a factor. Or if I do synthetic division, again, bring down the 1, multiply the 1 and the negative 3, add them, multiply, add, you get a 0, and this is our x minus 5 here that's left over. That 0 tells us indeed the x plus 3 was a factor. All right. Again, we have a couple more theorems to go through before we can bring this all together. The first is the fundamental theorem of algebra, which says if I have a polynomial to a certain degree, then it can be factored into that many linear terms. A linear term is when you have x to the first. So I can have x plus, I'll do a c, a number. So for example, if I had x to the fifth minus 4x cubed plus 5x minus 4, this would have 5 linear terms. Now they may not all be nice rational numbers like x plus 2, x plus 3, x minus 4. They could be square roots, they could be imaginary, but I would have 5 answers if I broke it down into all x to the first terms. All right. So then, along with that, it says, so if I do have that many linear terms, if I have an irrational root, which is a square root as a root, or an imaginary root, I have to, if I have a plus version, I have to have a minus version. So for example, if I had x plus square root of 5 is a root, then x minus square root of 5 has to be a root. If I had x plus 3i is a root, then I'd have to have x minus 3i as a root. And that comes from the quadratic formula, because if you remember the quadratic formula, negative b plus or minus square root 4, oops, sorry, got ahead of myself, b squared minus 4ac all over 2a. This plus or minus, if I can't do this square root, I have a plus and a minus from the quadratic formula. And so if it's a positive number under that square root, it would be the x plus rad 5 example. If I had a negative under square root, it would be the 3i example. All right. So now we're going to use this with the rational root theorem to be able to determine some values. So the rational root theorem gives all possible roots to a polynomial equation. So these are just guesses. We have to see which ones work. This will not give you irrational roots. Will not give irrational roots. So it is possible to have a polynomial. You list out all the possible roots and none of them worked because they have irrational roots. Now we're not going to be cruel like that and on a worksheet give you ones that none of the roots work, because that would be mean. But no, this is only for when you have rational roots. So if you have any square roots of, let's say square root of 5 was a root, that's not going to be found. All right, so let's go over how do you find your possible roots, and then we'll do, this will give us a complete look at how all these theorems come together. All right, so we want to get all possible roots. We're going to use the constant and the leading coefficient, which means the coefficient of the variable to the highest power. So we're going to use -2 and 15. All right. So we use variables to represent them. P is used for the constant and Q is used for the leading coefficient. Why is it reverse alphabetical? I don't know. All right, so you list all the possible values. So all the possible values of -2, are plus or minus 1, plus or minus 2. They're always going to be plus or minus because we don't know which one's positive, which one's negative, or if both are negative, both are positive, if it was a plus. So you're always going to do plus or minus. Then you do all the factors of the leading coefficient, and we divide. Now you might be saying, where did all this work come? Here, I will show you. So I'm going to take each of the numerators and divide it by the -1, and that gave me the plus or minus 1 and plus or minus 2. Then I'm going to divide them both by the 3. That gave me the 1/3 and the 2/3. Then I'm going to divide both by 5 and then both by 15. So this one has 16 possible zeros, and we would have to test all of them out. Well, not all of them. If you start with a cube, you only have to test until you find one that works, and then you'll be down to a quadratic, an x squared. And you could factor that, use quadratic formula. There's a bunch, complete the square. There's a bunch of different methods you have to solve a quadratic. This one, it ends up that -1, -1/3, and 2/5 work. In the next example, I'll show you how we figure that out. But I want to show you what those answers mean. So those answers mean, where is my function equal to 0? Where do I cross the x-axis? So what we're finding is those x-intercepts there. So our answers are where the graph crosses. And those are usually important points when we're talking real-world applications, because we want to know when things equal 0. All right, so let's try this one. We're going to find all possible solutions. So first I'm going to list my p's and my q's. It's always nice when q is a 1, because then it's just the factors of the constant, because when I divide by 1, it doesn't matter. All right, so these are our possible solutions. ±1, ±2, 3, and 6. All right. So I don't care about the q, and because p over q is just going to equal that since the q is 1. All right, so now we want to test the values out. And we're looking for which ones are actually roots, so our remainder is going to be 0. So I'm going to synthetically divide. I bring down the 1, multiply, -1, multiply, -6, and multiply, -6. Ooh, I found one right away, because this is a 0. Let's do -1 first. Let me go back, because I want you to see what happens if a root doesn't work. So 1, -1, -1, so this is -3. That gives me +3, gives me -2, gives me 2, that's 8. So if this is not 0, it's not a root, and you can cross it off your list. But I did get 1 to work first. So 1, let's double check I did it right. Yes. All right. So this leaves me then, because that's a 0, it means 1 is a factor. And we have x squared minus x minus 6 is our quadratic we're left with. Now you have to know if you're finding the factors or the roots. So if we're asked for the roots, we're going to give an x equals answer. So far we have 1. You don't want to forget the one that you found in your first step. Then I can factor this. So what multiplies -6 but adds to -1, that'd be -3 and 2. So then this would be x equals 3 and x equals -2. So those would be our other numbers. If we were asked for factors, so these are our roots, then we would want to give them as in parentheses. So our x minus 1 from the original discovery, and then x minus 3 and x plus 2. All right, and what does the answer mean? So here's graphically what it looks like. We have -2, 1, and 3. All right, so that is the rational root theorem. Feel free to go back and watch the end of that, especially for help on the worksheet if you need it. And I will see you back in class.